Welcome. Today is Monday, March 15th. The Ides of March.
Didn't Caesar
Beware the
Yes,
Ides
he
of
did.
March. Eat two fruit today.
Maybe something bad will happen today. Like,
Okay.
everyone is come back to
Mr.
school.
Sarah wrote that on our post today.
Yes. Beware the Ides of March.
That shouldn't be in the video, because then I could get like in trouble if something actually does happen.
Okay, so we're working on
Do it.
Friday, we started talking about equilibrium, stoichiometry, okay? And there are 4 steps to solving a stoichiometry problem, and that's pretty much where we ended up at the end of the day, is these 4 steps. So the first thing is you have to write a balanced equation, because that's the recipe in which everything's gonna combine, okay? That's essential. A lot of times it's given in the problem, but if not, we have to write a balanced equation, which is why we did writing and balancing equations before we did stoichiometry. Because it's the foundation on which everything works. Then you're going to be given some superfluous information, but we have to just kind of, I said on Friday, just the facts, ma'am, just the facts. You need to whittle it down to what am I given and what am I looking for? Because there is an old saying that I made up not too long ago that says that if you don't know what you're looking for, you'll probably never find it. Okay? If you don't know where you're going, you'll probably never get there. Deep Monday thoughts. Okay? All right. Then we determine the mole ratio from the balanced equation. That's just your coefficient, so it's always going to be unknown over known. Then we just solve the problem. So how do I go from massive given to moles of given? What do I use as my conversion factor? The molar mass of the given. I'm going to skip this. How do I go from moles then of unknown to mass of unknown? The molar mass of the unknown. Now in this case you're going to divide, in that case you're going to multiply because we're going the opposite directions, but the conversion factor is still going to be the same, the molar mass. But how do I go from moles of given to moles of unknown?
Mole ratio.
That's going to be your mole ratio. Some call it a mole bridge. Okay? It's the coefficients from the balanced equation. This is the new part. This is how we go from one thing to another thing. This is the conversion factor between hydrogen and oxygen when we're making water. Okay? So, if we want to look at an example, how many? We did like 2 examples already. One.
Wait,
It's just KClO3.
yeah.
That was the only example we've done.
Mm-hmm.
Okay, so let's look at then at the equation, the reaction of silver nitrate plus potassium chromate. 2 solutions that mix. So what's it going to make? AgCrO4, but what do we have to make sure we do? So we look on your periodic table and you see the charge for silver. Anyone got theirs out? Silver is going to be +1. Chromate, we look up here. It's right in the middle of the 3rd column. -2. So the formula is going to be, if this is +1 and this is -2, Ag2CrO4 plus what? KNO3, and again we have to balance the charge. What's the charge on K? What's the charge on NO3? -1. Okay? So I have to balance this.
2 in front of
A 2 here
K.
and a 2 there, right? And now finally we need the states of these. Which one of these would be aqueous? All alkali metals are soluble, all nitrates are soluble, so this is going to be my aqueous one, which means if this reaction occurs, which it does, you put, this is colorless, this is yellow, we get the red, tomato juicy red precipitate forming here. I did that as a demo for you in the last chapter. So this is my solid. So the question is, how many grams of Ag2CrO4 can be formed when 10 grams silver nitrate react with excess potassium chromate. So step one, I gave you the balanced equation. So what am I given, what am I looking for?
You're given 10 grams of silver nitrate.
Okay, so I like to write that right above what I'm given, 10 grams, and include the unit. And what am I looking for?
A silver chromate.
And then I want grams, so go ahead again, because sometimes it may ask for moles. It may ask for, could ask for ions, it could ask for anything, so we need to know what we're looking for. The units are gonna be really important on that, okay? So what's my mole ratio between the silver nitrate and the silver chromate? 2 to 1. Okay, so that third step is just kind of what we just looked. Once I have my balanced equation, I don't worry about these two things. I'm only interested in my given and my unknown. So I'm going to solve the problem starting with what's given. I'm going to start with 10 grams of silver nitrate. But now I need to convert that to moles of silver nitrate, because my balanced equation is a mole ratio. The 2 to 1's a mole ratio, not a gram ratio. So how do I convert silver nitrate to moles? The molar mass, okay? It's gonna be 107.9 plus 14.01 plus 48. It should be 169.91. Where does grams need to go? On the bottom, so we're gonna say 1 mole of 169, what did I say, 0.91? I said 7.8 or 9, and it's 8, it's 9. Okay, so if I stopped right there, what do I find?
The molar mass.
Well, that's the 169, but if I do this divided by this, I'm left with moles of silver nitrate to give. So I'm just going from here to here. What's the next step? Mole ratio. Okay, we just said it's 2 to 1, but which one goes on top, which one goes on bottom? If moles of silver nitrate's on top, where does it need to go to cancel? So we're going to say 1 mole Ag2CrO4 over 2 moles AgNO3. Moles of AgNO3 cancel. So if I stop right there, that's going to give me moles of unknown. But how do I go to grams? Well, of the unknown, which is the silver chromate, the Ag2CrO4. So somebody on a calculator put all these numbers in. 107.9 times 2 plus 52 plus 64.
331.8.
This time it's going to be on the top. And we get
9.76.
9.76. Two people agree on that number?
Yeah.
Too small. So you always want a unit and a label. Am I giving grams, am I giving moles, and of what? And everything else should cancel out. Notice that moles canceled here, leaving me with grams of silver chromate. So if I mix 10 grams of silver nitrate with plenty of potassium chromate, I can expect to get 9.76 grams of silver chromate precipitated out. I can collect that with filter paper and then weigh it, dry it and weigh it, then we can kind of compare. Okay? Now, in the Chemistry 1 class, the regular class, they say that there's 4 types of stoichiometry problems. There's really only one type. It's just where am I starting, where am I ending? But in the Chemistry 1, they say, okay, type 1 is just moles to moles. Well, that means I just have to do this one step. I just have to do the mole ratio. The second type is mass to moles. Mass of given to moles of unknown. So now I have 2 steps. The third one is moles are given to mass of unknown. And then the fourth one is the whole thing. But the reality is, it's just where am I starting, where am I ending on all of these. Does that make sense? So stoichiometry is really the only thing that's new for us is this ratio right here. We already knew how to convert grams to moles and moles to grams. We already know how to calculate the molecular mass. We know how to do all of that already. So now it's just, we're putting it all kind of together with an equation into stoichiometry. Okay? Now, let's just say that I go and do this lab. Okay? I actually used to do this one, but silver nitrate's very expensive. The cost of silver is going way up. So we can't do this nice, pretty one. We're going to do a lab probably on Thursday. That'll take about half the period. But we're just going to make a white solid instead of a nice, colorful red one. But we're going to filter it, dry it, and weigh it. Okay? So let's just say when a student performed this reaction and collected the Ag2CrO4 I don't want to be he or she, it doesn't matter, he, she, okay, collected 9.25 grams. What is the percent yield? What do you think that is? How would we get percent yield if?
A percentage of all the other ones.
Okay.
Like out of the total reactant.
Kind of.
How much?
Percent yield.
Is it percent error?
It's kind of the converse of percent error. Okay? Percent error is how much you miss by. Okay, so I go and I make cookies. I'm pretty good at making an oatmeal chocolate chip cookie. And if I do the recipe right, it'll make 36 cookies. But most of the time, I only end up getting 33. Mainly because I eat a lot of the cookie dough. Okay? So, but my yield, if I didn't eat the cookie dough, I would get 36. That's the maximum I could and should get. But I'm only getting 33. So what's my percent yield going to be? 33 over 36, right? Well, the stoichiometry tells me how much I should get if everything is done perfectly. This is what I really got, my actual yield. So what's the percent yield going to be on this?
9.25.
So the percent yield is going to equal the actual yield. In other words, what you really got, your experimental yield divided by the theoretical yield. okay, times 100. And this theoretical yield is, you always get it from stoichiometry. This one is generally given. So here we're going to say 9.25 grams divided by the 9.76 grams times 100. So the percent yield equals
0.95.
you got to multiply by 100. 94.7.
8.
So 94.8 since there's 3 sig fig. Percent yield. Okay, so when we're doing stoichiometry, it's always going to give you the maximum amount. If everything is done perfectly, that's what you should get. But we know life isn't always perfect and labs don't always go perfectly. So we calculate our percent yield. In industry, what a chemical engineer is going to do in a process is, okay, we have to figure out in stoichiometry, we got to figure out, well, how much raw material do I need to bring in? What's the ratio in which I need to combine those? And then what's my expected yield? What should I get? And then they're actually doing the process and measuring how much they're getting, and they're trying to maximize this yield because anything less than 100% is generally waste or loss, and they're not making money off of it. So a chemical engineer is going to try to, figure out the conditions and how can they do the reaction to where they can increase their yield. What's causing the loss? That's what one small fraction of what a chemical engineer could do. All right? So, does anybody have any questions just on straight up stoichiometry? Let's look at, we only have one more type of problem, one more kind of a add-on problem to this. And then we'll just spend today and tomorrow doing practice problems the rest of the time. Just making sure we're good with this. Thursday we'll do a lab and kind of go over any practice problems that we have. Friday you're going to have a test over equations and stoichiometry.
Yay.
Okay? And then
Wait, is equations what we just did?
the quiz on, yeah. But it's going to be a little bit more, extensive. And I really want to make sure we can do total and net ionic equations because that's what people struggle with the most. Okay? All right. Okay, when I'm erasing the board, that's when you stretch and you breathe and you get yourself refocused.
Or start.
Yeah. I'm gonna leave that up.
Okay.
I'm gonna go to the magic closet of science.
Will we ever watch another Bill Nye? We might have to just go to YouTube. A magical whiskey jar of science.
It's a bell jar, it's not a whiskey jar, it's what you put preserves in.
Yeah, Clay.
It's not moonshine bottle. You from Tennessee? All right, so if I,
I do not know.
there we go.
There's like 50 of those at my grandmother's house.
Because that's not probably making moonshine. Hopefully. So if I let this candle burn right now, when is the candle going to go out?
When the wax is melted and the
When
wax
oxygen
is
goes away.
Okay? Well, which one's going to run out first, you think? The wax or the oxygen?
Wax.
Wax.
The wax, okay. Just for the record, it's the wax that's burning. It's not the wick. Now, the wick does burn, but the wick just burns down to the level that the wax rises up in it. Okay, so the wax, you light it, the wax melts, it rises up into the wick, the wax is burning, and then the wick burns down to the level, the wax only goes up a little bit into the wick, so it just kind of keeps burning down. But it's definitely the wax that's burning, because when this is done, there's no wax left. Where's it going?
Evaporate.
Evaporating?
Some of it
Melting.
melts.
Wax, let me just tell you this, wax is a hydrocarbon.
Turns to water and then you.
It's making carbon dioxide and water. Now, this is incomplete combustion, so you can see the black sometimes around here. You can see the black on this. So what's that black on here?
Straight water.
That's straight carbon, that's soot, okay? So we're getting incomplete combustion. So this candle will continue to burn until all the wax runs out because there's plenty of oxygen. But if I put the lid onto it, now what's gonna happen?
Go out, because all the oxygen's gonna burn to the oxygen.
It's gonna burn until the oxygen runs out, and it's getting fainter and fainter and fainter.
That's so depressing.
I can't breathe. All right, so it's hot. Okay, so it goes out. Okay, so it goes. It was hot. So it goes out when all the oxygen is burned. Okay, so the oxygen was what we call the limiting reactant. What do you think the limiting reactant does?
Limits
Limits
the
the
amount.
amount.
Limits the reaction. It's a very creative name. And which one is going to be the limiting reactant? Well, just in general,
The one that
There's the
really
least amount of,
controls.
least amount of.
the least amount, the one that runs out first. Okay? The limiting reactant. The reactant which runs out first. And limits the amount of product made. Okay? Because once it goes out, there's no more CO2, no more water being made because there's no more oxygen. There's plenty of wax left, there just wasn't enough oxygen. Okay? So the limiting reactant, it runs out. It's the one that limits the reaction. So how do we calculate the limiting reactant? How many grams of PbI2 can be formed when 10 grams of Ki react with 15 grams of PbNO3 Looks like a stoichiometry problem. So what's the first step we should do? So what's going to react with what? Ki, both of these are going to be aqueous, plus PbNO3 And what's that going to make?
PbI2.
PbI2, because it's plus 2. Do the reverse crisscross here. We know lead's going to be plus 2, nitrate's minus 1. So we're going to get PbI2 plus KNO3. And I already said that that was going to be the solid, but we would know that this one was aqueous because it's an alkali metal and it's a nitrate. So I have to balance this by doing
2 on the Ki, 2 on the KN.
2 and 2. Now this time we say, okay, so now what's my given, what's my unknown? Well, my given is 10 grams of this and 15 grams of this. And I want to know how many grams of that, right? But how do I know? I'm supposed to start with what's given here, but I have two givens. So we got to figure out, well, which one of these is the limiting reactant? The first thing is we're going to recognize it's a limiting reactant when a quantity, a mass or moles of both reactants are given. here, notice on the previous example, I said so many grams reacted with excess. Okay, meaning we had plenty, and so that tells me that the thing I gave you the grams of is my limiting reactant because I had excess of the other one. So I have to figure out, well, for every mole of this, I need 2 moles of that. So I need to know, do I have 2 moles? Is 10 grams 2 moles? You know, twice as many moles as however many 15 grams is of this one. So yeah, in other words, we have to convert each to moles. It's a mole ratio. So I'm going to take 10 grams of Ki times 1 mole over iodine's 127, 126.9 plus 39.1. So 27 and 39 is 5766. Okay? Somebody type that in. So that's how many moles of Ki I have. I gotta see if I have twice as many moles of this, because I can't just say 10 grams, 15 grams, because they weigh different amounts. It's a mole ratio. So I gotta now do the same thing. 15 grams Pb NO3 2 times 1 mole over, somebody want to type in all these numbers? 207.2 plus 28.02 plus 96. 331.
331.22.
And that turns out to equal
0.045.
for the green 5, is it 5?
5.3.
5.3. 3 sig figs. Okay, so this is how many moles of lead nitrate I have. This is how many moles of Ki, but it's not a 1-to-1 ratio. I need twice as many. Do I have twice as many moles? No, because twice as many would be 0.9, or right, or 0.09. But the way we can figure this out is always just divide by the coefficient in front of E, divide by 2, divide by 1. Obviously this is still 0.0453. Divide this by 2, it's going to be 0.0301. This is the smaller number, therefore this is my limiting reactant. Now, many, probably most teachers will just tell you to take grams of this all the way to moles of this, and this one go all the way to moles or grams of this, and whichever one is the smallest, that was your limiting reactant. I just think that we can cut off a bunch of steps by doing it this way. Okay? Now you have to realize this is the moles. This number is really a nothing. This is just our ratio to find out if we're in a ratio. So now I still have to answer my question. Now I just know that this is my limiting reactant. It's the one that's going to determine how much product gets made. Because when it runs out, the reaction stops. Doesn't matter how much of this we have, this one's going to limit the reaction. So I start with that. Now I've already converted it to moles. Okay, so I can start right here at 0.0602 moles of Ki. But what's the question asking for?
Grams of PBI2.
Grams of PBI2, right? So I'm really starting right here. I need to go to moles of PBI2 to grams of PBI2, right? So how do I go from moles of Ki to moles of PbNO3
Mole ratio.
which is going to be 1 mole PbI2 for every 2 moles of Ki. Moles of Ki cancel. So, but I need grams. How do I go to grams of PbI2?
1 mole over
Well, where does moles need to go this time?
the bottom.
On the bottom, so put the grams on the top. So 207.2 plus 126.9 times 2,
461.
461 grams over 1 mole. Moles cancel, we're left with grams of PbI2. And all of that's gonna end up equaling
13.87.
19.87,
13.
13.87, 13.9. That would be my theoretical yield of lead iodide, lead 2 iodide that can be formed. Okay? So if I did everything right, I mixed these things together, everything right, but in my beaker, okay, I pour the Ki in, and I pour the PbNO3 in, okay, they react. I'm gonna make some PbI2 solid. It's gonna settle out to the bottom. What's gonna be floating around in the liquid?
The separate Ks.
Oh, sorry.
Well, the KNO3s, right? So I'm gonna have K pluses floating around. I'm gonna have NO3 minuses floating around. But what else?
PbNO3.
Some of the excess of this is still gonna be floating around, right? So more NO3s, but I'm gonna have some Pb2 plus still in solution, because it was excess. So now the last question. How much excess was there? How much Pb was left over? Okay?
1.1.
Now, because you don't know how many potassium nitrate was made, we haven't figured that. Okay? All we have to do now on this one is make this one my unknown. Just say, y grams of this. What's that gonna tell me if I solve for that? Well, we're gonna use the molar mass,
How
but
many grams would make 10 grams?
how many grams were needed to react with the 10 grams? This is how much was gonna get used. So what's the excess gonna be?
Oh, it didn't get used.
What didn't get used, the difference between the two, right? So we always just, when you find the excess, we do the limiting reactant. I know that this one is limiting, okay, Lr, and this one is excess, okay? So I just make this my unknown and find out, well, how much of my excess actually got used? So I do the exact same thing, 0.0602 moles. You always use the limiting reactant. Now the mole ratio between these two, again, it's 1 mole PbNO3 for every 2 moles of Ki. Now we've already done the molar mass, 331.22. So what's that gonna get me?
9.97.
That's pretty good.
I saw that, that's a nice shot.
9.97 grams PbNO3. And what is that again? What's that represent? What is that number?
The stuff that wasn't used,
Not the excess.
the part that it took to use.
This is the part that got used. Okay? So excess
Would be 15 minus that.
is always gonna be the given minus the used, which is gonna equal the 15 grams minus the 9.97 grams, which is gonna equal 5.03 grams excess PB NO3 2. Which means that it really takes about 10 and 10 grams of each one, because the molar mass of the lead nitrate is just about double the molar mass of the Ki. So, what we need to be able to do in terms of stoichiometry, we need to be able to follow the yellow brick road. We need to be able to go, given one thing, find the others, okay? What are our mole ratios? If you're given moles, looking for moles, you only have to do this one step, okay? Sometimes you'll be given both reactants and we have to determine the limiting reactant. Convert each to moles, divide by the smallest one's the limiting reactant, then use it to do all the other stoichiometry. Always use the limiting reactant. And then to find the percent yield, we just put the given actual yield over the theoretical stoichiometry theoretical yield, and we get the percent yield. And then we should also be able to calculate how much excess reactant there is. Okay? Nothing super complex here. We just got to keep our steps right. So, let's look in your textbook, which we don't do very often. We are in chapter 8. This is chapter 7, Introduction to Stoichiometry. We'll do some together here, and then tomorrow is going to be a total work day. Okay, I am on page 311. Page 311. So let's just start off simple. Number 5. Hydrogen and oxygen react under a specific set of conditions to produce water according to the following equation. Very common. How many moles of hydrogen would be required to produce 5 moles of water? Well, what's the mole ratio? Hydrogen to water. Not 2 to 1. 2 to 2. Same as 1 to 1. Okay? So if I want to do this mathematically, I'll try and do it over here. I don't need much space. Can the camera see over here, Caroline?
Yeah.
So if I start with 5 moles of water, that's my given. Okay, people are going to get dizzy over here. I'm given moles of given. What am I looking for? Moles of unknown. So the only thing I need is this mole ratio, which is always the given and the unknown. This is the given, this is the unknown. So I say 2 moles of hydrogen for every 2 moles of water. And the very high complex math says, well, I'm going to need 4 or 5 moles of hydrogen. But these you should be able to just do by inspection, just looking. You really don't need to write these down because it's just going to be a simple ratio. So, how many moles of oxygen would be required? Well, we're still again making 5 moles. Right? What's the mole ratio?
1 to 2.
1 to 2. So how many, to make 5 moles of water, how many moles of oxygen do I need? 2.5. Okay? So mole to mole rate, mole to mole problems are just this mole ratio. Okay? Just the mole ratio. And that's always from the balanced equation. That's why you have to have a balanced equation. So, you try to do number 6. Now notice the words in here, it says unbalanced equation. So the first thing we got to do is balance it. Okay, so did we get it balanced? Do we have to double everything? Put a 2, 6 makes a 3, that gives me 4, 3 makes 7, so I do need to double 2, 4, 6, that makes 8, and 6 makes 14, so I need a 7. So, I have 4.5 moles of this. What's the question asking for first? How many moles of oxygen? So again, it's just moles to moles. So I start with my given, 4.5 moles of ethane. What's my mole ratio? 7 to 2, right? And I always want the unknown over the known because I want moles of ethane to cancel out. So moles of ethane is going to go on the bottom, moles of oxygen is going to go on the top. So I'm going to say 7 moles of O2 for every 2 moles C2H6. Moles of C2H6 cancel. So it's 28 and then 3.5, 31.5 divided by 2 goes to 15 point. I was getting there. 15.75. Really, with 3 sig figs, we'd say 15.8. So moles to moles is just the ratio. So now sodium chloride is produced from the elements through a synthesis reaction. What mass of each reactant would be required to produce 25 moles? So this one now, you're given moles and you're looking for mass. Now notice they give you the moles of products. It doesn't matter which way you go. You can go products to reactants, reactants to products. You have a given and an unknown. It doesn't matter which way you go. So tomorrow we're going to go through and you're just going to get to practice all of these. Now, don't lose track of all of the balancing equation stuff either. Okay? So tomorrow is going to be that Thursday. We're going to do a lab, and then we should have some time at the end to review. The lab's pretty quick. Okay? And then test will be on Friday.